Now that we've talked about how the solar system formed, it's time to start talking about each of the planets. And like we did with the sun and stars and the Milky Way galaxy and galaxies in general, we're going to start with the planet that we know the best, which is the Earth. So first, let's talk about the interior of the Earth. So how is it that we know anything about the interior of the Earth? The evidence that gives us our ideas of what's happening under the ground and through the center of the Earth come from several different places. One, we have inferences from meteorites. Remember, a meteorite is a lump of rock from space that has fallen to the Earth. Second, we actually have evidence from the Earth's mass and density. Third, we have a lot of evidence of what's going on from seismology. Seismology is the study of earthquake waves. And then last, the fact that the Earth has a magnetic field actually tells us something about the Earth's interior. So first, meteorites. Again, a meteorite is a lump of rock from space. So how is it that a lump of rock from space could actually tell us anything about the Earth? Well, the Earth is essentially a giant lump of rock in space. Meteorites formed in the same way as the Earth did at the same time, so it's going to tell us something about composition. As we look at different types of meteorites, we find that there are some meteorites referred to as stony, which are made of rock. There are some that are made of metal, referred to often as iron meteorites because it's predominantly iron, and then we find some that are a mixture of both stone and iron. That indicates to us that the Earth is probably made up of rock and metal. Here is our first lecture quiz question. The surface of the Earth has a density of about 3,000 kilograms per meter cubed, but the average density is around 5,515 kilograms per meter cubed. This means the interior of the Earth must be A, as dense as the crust, B, denser than the crust, C, less dense than the crust, or D, there's no way to tell. Go ahead and think about it, and we'll discuss in just a bit. So if the average is around 5,000, but we know that the crust is only 3,000, this means that the interior must be B, denser than the crust. So from this sort of density consideration, we start to get the idea that the interior has to be denser. If the interior of the Earth has a sufficient amount of iron and nickel compared to the amount of rock, then we can get to this correct density that we need. Something that is comforting is that the ratio of rock to metal for the Earth to get to the right density actually agrees with the proportions of rock to metal in meteorites that we find. So we actually have two sources telling us about the composition of the Earth. Just knowing the density and composition doesn't actually tell us anything about the structure of the interior of the Earth. To figure out structure, we look at seismic waves. There are three types of waves. There are surface waves, compression, pressure, or longitudinal waves. Those are three names for the same type of wave, and then there are shear or transverse waves. That's two names for the same kind of wave. Surface waves only travel along the surface of a material, which means that it's not going to tell us anything about the interior. So it exists, but it's not going to help us in any way. Compression, pressure, or longitudinal waves displace the medium in the same direction that the wave travels. So that's what we have going on up here in the upper image. The hand is moving in and out, and as it does, it's going to cause the spring to get compressed and stretched out. These compression and rarefaction regions, that's rarefaction is this region where it's spread out, will travel down along the spring. So the material is actually squeezing and stretching apart as the wave is traveling through. Now this type of wave is able to travel through any state of matter. Solid, liquid, gas, it doesn't matter. As long as there's a material there, this wave is going to be able to travel through it. These are sometimes referred to as primary waves because they're the first ones to arrive. These travel the fastest. Okay, so primary or P. Notice, primary, P, pressure. Okay, that's something that helped me when I was getting through all this the first time. One example of a P wave is sound. Okay, as sound travels, it's actually compressions and stretches in the air that lead to slight pressure differences, and it's those changes in pressure that actually cause your eardrum to vibrate back and forth. The other type of wave that actually travels through the body of the material is a shear or transverse. Now for me, this is usually what I think of when I think wave. This is where the material moves perpendicular to the wave motion. So it's the hand on the string. The string is going up and down, creating these peaks and valleys. And these peaks and valleys are traveling to the right in this case. Now this type of wave is only able to travel through a solid. Only a solid has a strong connection so that as one part goes up, it's able to drag the next part up with it. Now these are known as secondary waves because they are the second one to arrive after an earthquake. So they're also referred to as S. So notice S, secondary, shear, only go through solids. Now the motion of a guitar string or anything like that is going to be an S-type wave. So the way that we actually use these, we can't follow the wave itself, so instead we find where they hit on the surface of the Earth. If you remember back when we were talking about lenses, we mentioned how when light goes from one material to another, it bends. That's not true of light, it's true of all different types of waves. So, as these waves travel through the Earth, if they hit a sudden change in density, they will bend, and then, because of those bends, we'll detect the wave at different locations on the surface of the Earth. So, for example, starting with the earthquake, traveling along, notice that this green line is able to keep going. There is a slight bend to it because of slight changes in density, but the blue wave right next to it hits a very sudden change in density and has a very strong bend to it. And because of these strong bends, there gets to be a gap in between those two waves. They started out right next to each other, but over here, where they actually reach the other side of the Earth, there is a gap. This gap, where we do not detect earthquake waves, is known as a shadow zone. These shadow zones, what we do is we see where the shadow zones are located on the surface of the Earth, and then we trace backward, saying how did this wave have to refract to get the shadow zone that we're actually seeing. The shadow zones we're seeing in the P waves are showing that there is layering in the interior of the Earth, that there's actually structural layers. When we look at the S waves, so in this image, the green are the S waves, there's a huge gap that covers almost half of the Earth. This indicates that the S waves are being completely blocked. Well, the only thing that we know of that can completely block S waves is a region that is not a solid. Remember, S waves only travel through solids. So this indicates that there's also a liquid layer within the interior of the Earth. So putting together everything that we've talked about so far with composition and structure, we think we have a pretty good idea of the structure of the interior of the Earth. Starting at the very center, we have the core. Now the core is made up of iron and nickel, and it's separated into two distinct layers. There is the inner core, which is solid, and then surrounding the inner core we have the outer core, which is liquid. So the inner core is solid iron and nickel. The outer core is liquid iron and nickel. Surrounding the core we have the mantle. The mantle is made up of plastic rock. What we mean by plastic in this case is moldable. This stuff, with pressure pushed on it, will actually flow. So think something like clay or Play-Doh. It's a solid, but if you squish it, it squishes. Then the last layer is the crust, which is also rock, but in this case it is rigid rock, meaning that it is going to break instead of bend. Now notice, when talking about the inner and outer core, the inner core is solid and the outer core is liquid. But as we get deeper and deeper into the Earth, we actually get to hotter and hotter temperatures. What this means is that the inner core is actually hotter than the outer core, and yet it is a solid. Now what's going on in this case is whether something is a solid, a liquid, or gas is not just determined by temperature, it's also determined by pressure. So although the inner core is hotter than the outer core, there's so much more pressure on it that the inner core has actually turned into a solid. So the inner core is a solid because of the intense pressure. Then, as we transition from the inner core to the outer core, the pressure decreases enough that although it is cooler, it is actually a liquid. Now, because of the temperature differences from the bottom of the outer core to the top of the outer core, and then also the temperature difference from the bottom of the mantle to the top of the mantle, this can actually create convective cells. Now, we've mentioned convection previously, but as a review, the idea is that we have some material where on bottom it's hot and on top it's cool. If the bottom is hot, then as it heats up, it's going to expand, and as it expands, it becomes less dense. When it's less dense than the stuff around it, it's going to rise up. As it rises, it's going to get to a cooler region where it's going to lose that heat, and as it cools off, it's going to compress. As it compresses, it becomes more dense, and because it's more dense than the surroundings, it's going to sink again, restarting the cycle. So we actually have convective cycles within the outer core and also throughout the mantle. One last evidence we can use to help us understand the interior of the Earth is the fact that the Earth has a magnetic field. For any object to have a magnetic field, to generate its own magnetic field, there are three things that have to be true. There has to be an electrically conducting liquid in the interior, that region must have convection, and the planet has to rotate fast enough. Well, the fact that the Earth has a magnetic field means that all of these are true. So for the Earth, what's going on is we have liquid iron, which is a good conductor of electricity. And this is part of the outer core, which there's enough temperature difference to lead to convection, and the Earth rotates once on its axis every day, which is absolutely fast enough. So this tells us that our ideas of the outer core are correct. Here is our second lecture quiz question. How do we know the structure of the interior of the Earth? A, we have drilled exploratory holes to the center of the Earth. B, we look for shadow zones in seismic waves indicating how they have refracted. Or C, by looking at the structure of meteorites. Go ahead and think about it, and we'll discuss in just a bit. Alright, so how do we know the structure? We know the structure from shadow zones. Meteorites tell us about the composition, what it's made of, but shadow zones tell us about the structure. So the correct answer is B.